All right, hi everyone. So Jillian and I will be presenting our project, which studied hurricane risk along the West Florida coast. So our client was Jeff Berardelli. He's a chief meteorologist and climate specialist at WFLA-TV in Tampa, Florida, and he's also an alum of the Climate and Society program. And our work was conducted under two scientists at Lamont, Dr. Susanna Camargo and Dr. Chia-Ying Lee. So Tampa Bay is arguably one of the most at-risk cities in America to a major hurricane making landfall. It has over 700 miles of exposed shoreline, over 3 million residents, and $150 billion worth of property at risk. And so a major hurricane making a direct hit on the Tampa Bay area would surely be a very horrible disaster. However, Tampa Bay hasn't been hit by a major hurricane in over 100 years. And the last major hurricane that made landfall was in October of 1921 as a Category 3 hurricane. And so globally, we can use the term tropical cyclone, but here we'll be discussing hurricanes, which form exclusively in the Atlantic Basin and as categories 1 through 5 on the Saffir-Simpson wind scale, which we'll discuss in a bit. Hurricanes are rapidly rotating storm systems characterized by a low pressure center, a closed low level atmospheric circulation, strong winds, and a spiral arrangement. And so the goal of our project is to understand if Tampa has just been lucky over the past 100 years, or if the region is insulated by climate or geography. So, Hurricane Ian made landfall in 2022 in Fort Myers, Florida, just south of Tampa, and was really one of the most destructive and costliest storms in the United States and really shocked the state of Florida. And after this event, our client, Jeff Berardelli, became curious about Tampa Bay's precise risk of being hit by a major hurricane and reached out to scientists at Lamont and asked if a team could potentially quantify Tampa Bay's chances of being hit by a major storm. So that his team at WFLA-TV can educate people and help prepare them from what might happen during hurricane season, which runs from June 1st to November 30th. So getting into kind of the climatology of Tampa Bay, its location on the west coast of Florida, coupled with the direction of the prevailing winds at this latitude, which I'll discuss in a second, make the region difficult for a major storm to make landfall at high wind speeds. So the structure of the bay along the Florida coast is so that any storm that hits it will first kind of be interrupted by the landmass that St. Petersburg lands on. And in order for a storm to enter the bay uninhibited by any kind of landmass, it would have to enter at a very particular angle, as you can see, in order for the strongest point of the storm, the center, to remain above water, to retain its strength. It would have to enter at a very particular angle. And then also at this latitude, prevailing winds flow from east to west and could work against a low pressure system flowing in from the Gulf, which is where the major hurricane that I mentioned, the last one that hit in 1921, was fueled. So the first step in our methodology was defining our study site areas. We chose 4 study areas to compare with Tampa Bay. So we chose Tampa, Miami, New Orleans, and then all of Florida. And around each city, we chose an 150-kilometer buffer zone. And around all of Florida, we chose a 500-kilometer buffer zone. And we wanted to compare Tampa to other cities in the Atlantic Basin, which consists of the Atlantic Ocean, Caribbean Sea, and the Gulf of Mexico. And like I said, each circle represents a buffer zone, which our storm counts are based off of the storms that enters through each buffer zone. And so for our data, we used the National Hurricane Center's Best Track database, which is an analysis of all tropical cyclones over time. And here are some of the important variables that we use to determine our counts of storms. And we focused on all storms that were classified as tropical storms or greater in terms of maximum sustained wind speed. And we used the Saffir-Simpson hurricane wind scale with categories 3 through 5 denoting major hurricanes.
Okay, so the other half of data that we used to quantify Tampa's risk of being hit by a hurricane is the Columbia Hazard Model, which is a downscaling model of a global climate model that essentially lets us replicate storms moving across the Atlantic, and in our data that we used, it consisted of 1,116 storms being subjected to 40 different wind intensity ensembles, and those runs were run 40 different times for a grand total of over 1.7 million storms, simulated storms that we had to cycle through. So we had ample amounts of synthetic data to work with. So these are a couple maps of just some examples of the historical actual storms that took place in the area. So on the left, we have the major hurricanes that have interacted with that buffer zone we spoke about earlier with the Tampa Bay area. As you can see, there's only 6 of them. And in comparison, on the right, you have Miami, Florida. So you can see that in the same time scale, which is from 1851 to 2022, there were far more storms that interacted with Miami than there are with Tampa, which is to be expected. When you think of major hurricanes hitting Florida, you think about places like Miami and the East Coast, which makes sense. And this map is just showing examples of the simulated storms that I referenced earlier. So this is just 25 random storms that were taken out of the data set, just so you can see that we're getting the same sort of information. We're getting latitude and longitude points associated with wind speed and different variables such as relative humidity and things of that nature. So we're getting the same kind of information, but again, this is all synthetic data, just using downscale global climate model. So one of the things that we think about when we want to understand what risk is we want to know patterns, right? We want to understand what variables are existing at times that can kind of produce a pattern for us to be wary of and cognizant of when trying to understand when storms are going to hit and how bad they're going to be. Some things that you might take into account when considering this are things such as the sea surface temperature of any given location. What are the El Nino patterns occurring in the Pacific at the time, which can affect the global climate or the global ocean, and what are some atmospheric conditions, things of that nature. So a example of what you would think would be perfect things to show against each other to try and find one of these patterns would be these 2 storms, Hurricane Ian and Hurricane Charlie. As you can see, they had a very similar development as far as when they switched from different categories of storms. They went about, the approximate same kind of path. And you would think that they'd be 2 good storms to kind of compare to one another. But as you can see here, there were different ENSO events occurring at the time that these storms came through. They occurred at different times of the year. And also, it's important to note, as we all know, that like 2 storms that look similar does not a pattern make. It does not a trend make. And that's an important theme that we were encountering, was that a lack of data availability is what really limits us from being able to say what risk really is. So one of the ways that we overcame this issue of a lack of historical data was using those synthetic storms that I referenced earlier. So it just gave us a lot more information to work with. So from that, what we were able to do was to create return periods, which are essentially just saying what are the odds that a storm of a certain magnitude is going to occur at any given point in time, right? So, you can think of this similar to like with 100-year floodplains, right? It's not that a storm is going to, a flood is going to happen every 100 years. It is that there is a 1% chance every year that a flood of that magnitude would take place. It's the same idea with these storms here. So these plots are showing, the black line shows the return periods that we would anticipate based on the historical observations of the real storms. And the gray spread is what we would anticipate the return periods to be based on those synthetic storms that I referenced. The reason there's more of the gray spread is because we said there were 40 iterations of these storms ran. So we just had 40 different instances, and they're all going to produce slightly different numbers. So one of the things to remember here is that there's going to be a little bit of deviation just based on what amount of data you're working with. So, for instance, in Tampa, we only had 82 storms that crossed the buffer zone in the historical time period to be able to base this return period off of. However, for the replicated storms, there was over 60,000 to base these numbers on. So we can be a little bit more confident in the simulated return period than we can in historical, just based on skew of data. So yeah, it was really interesting to see that they lined up pretty well in Tampa and a little less well in Miami, even given that we'd have more storms in the historical record in Miami. So this kind of gets to the point of what is Tampa's risk of experiencing a given hurricane of a given strength in any year, right? So based on our historical observations, we would expect to see a Category 4 hurricane, for instance, every like 60 years or so. Again, this is just, based on, this is like transferring that into like the percentages and things. But what you can see here is that 0 denotes that in our historical observations, there is not a single instance of a Category 5 hurricane interacting with that buffer zone in Tampa. So we cannot say, based on the historical record, what we would expect it to be because it's never existed in the record. So we can't interpolate that. But we overcome that problem by using the synthetic hurricanes. So like I said, we're looking at over 60,000 of them in comparison to less than 100. And during that spread of data, we would anticipate that at least one of them would be a Category 5 hurricane, which helps us overcome this. So we would anticipate seeing a Category 5 hurricane in Tampa every 620 years or so. And again, you can see that these numbers match up a lot better in Tampa than they do in Miami, which is just kind of like reflects those plots that I showed earlier.
So our final deliverable to our client was an interview on his show called Jeff's Climate Classroom. And I was interviewed along with one of the scientists at Lamont, and we kind of answered some questions regarding the motivations of our project and kind of the goals. So going forward, consensus projections of future tropical cyclone behavior globally indicate increases in maximum intensities and peak and mean wind speeds, and that future sea level rise will exacerbate the impacts of storm surge on coastal regions. However, when we go from like global to regional projections, confidence levels decrease, and so there isn't consensus on what is causing tropical cyclone variants in the Atlantic Basin in particular. However, there is consensus that globally they will become more intense, which is something to keep in mind when considering Tampa Bay's risk. And we haven't touched on this, but one of the initial desires of the project was to examine Tampa's risk under climate change compared to other cities. So this is something that could be done going forward. And here's a quick summary. We have, a better understanding of Tampa's geography and climatology and why a storm might have difficulty entering the bay. We have some ideas of when Tampa might expect to experience a major hurricane. And then going forward, the CHAS model can be used to consider how various emission scenarios might impact the formation of storms, and we can also possibly consider the socioeconomic impacts of how a major storm will impact the Tampa Bay area specifically. And that's all. Thanks.
That was really cool. I love seeing kind of how you used all the regression models we learned. But I was wondering, because like you said, so Tampa probably won't experience it, but you said that the landmass of St. Petersburg, it seems to be like right there. I'm wondering if your research, has anyone brought up maybe applying it to like that city? Are they worried? I feel like they should be worried.
I don't know if Jeff is worried about he was worried about Tampa Bay specifically, so that's what we looked at. So I don't know.
And it is important to know that this model in particular has been used to look at things like this in other places. So for instance, some of our literature review were in places like Texas, places like New York as well, in Mumbai, correct? So it has been used to look in other places, which kind of makes it flexible. So yeah, I think that this kind of idea can be used in a multitude of different places. So
that was so cool. But also, and this may be completely outside of the scope of what you have done, but I was curious, how difficult would it be to feed emission scenarios into the model to arrive at data? That it's just curiosity, wild curiosity, that's all.
Yeah. I personally do not know necessarily how difficult it would be. However, my understanding is that since Chaz is just a downscaling model, that you can use different global climate models to plug into Chaz, essentially. So the one that we used was the ERA5 model, which comes from Copernicus in Europe somewhere. I cannot remember off the top of my head. So depending on which CGM you're feeding into it, they all build, the world in a different way. They all are trying to reflect different things in the model. So depending on which one you plug in, I'm sure they could be used to use different emission scenarios. Yeah.
Just fascinating and wonderful to see this collaboration with, by the way, CNS alum who's now really not only getting word out with the weather every evening, but building kind of climate change awareness and really pointing, I think, to the idea of the scale of concern. It's one of the things that's coming up through a number of these talks, some of them more sciencey, some of them more policy, on how local both impacts and responses are. And, just fascinating to, we're seeing all the stories of this is a summer with really high sea surface temperatures just worldwide. And so Florida, which has very high sea surface temperatures, facing all this coral die-offs, isn't getting so many hurricanes so far, thank God, but might be due to other questions of El Nino or winds, but just how, I guess just in that sense, even though this one seems like a more science-y project and the others have been more policy, how really they're all working with local clients and how impressive that is to see.